Guys, it's Mr. Sims here. I know with everything going on this week, it's going to be kind of a crazy week. A lot of you have already reached out and just kind of said you're having issues here or there. I know Wi-Fi and electricity is kind of down in certain spots, so um, please, if you're running into those issues, please reach out and let me know. I would with the way the week is, I don't know what it's going to look like. I don't know what I'm going to take for a grade. It might be as simple as a participation. It could be maybe just a few problems on like a Friday or something. I'm not totally sure yet. So um, the tricky part is obviously that if you kind of miss a day, considering our block schedule, it's kind of like missing 2 days. So we want to kind of avoid that as much as possible. So um, again, my hope is that you can at least follow along, try and do the work as best you can, and kind of go from there. My plan is to offer tutorials each day from about 10 to 11 a.m. That allows us to, allows you to kind of come in, ask any questions, and so on and so forth. That will start tomorrow, though. That won't be today. All right, we're going to start that tomorrow. That way, kids have enough time to kind of get situated, and we can kind of go from there. All right. Well, let's go ahead and let's get started here. So on these first 7 problems, really what we're looking at here is sort of a review. So the first one is use the information provided to write the intercept form equation of each parabola. So what are we going to do first? Well, first thing we're going to do is we're going to take out this x plus 9 squared. Now again, I'm still seeing a few mistakes regarding order of operations, like kids want to distribute the 2 here, which isn't good math. Or they want to take this negative in front and distribute that as well. Again, you want to focus on squaring it. This is a binomial times a binomial, which means we go x to x and then x to 9, our double distribution here. So this becomes x times x, which is x squared, and then x times 9, which is plus 9x. We do the same thing with the other part of the binomial in the front. 9 to x, which is 9x, and then 9 times 9, which is 81. So what do? We combine like terms in the middle here, and we get x squared plus 18x plus 81. And so we take this piece that we have here and we bring it over back into our problem. So this becomes y equals negative x squared plus 18x plus 81 in parentheses, and then there's a plus 1 hanging out here at the end. So we're going to distribute this negative here, which isn't going to do a whole lot but flip our sign. So this problem becomes y equals negative x squared minus 18x minus 81, and then don't forget the plus 1 hanging out on the end. Again, this is what you get after you distribute that negative. And so what does this simplify to? Well, it simplifies to y equals negative x squared minus 18x minus 80. Why? Because we have a negative 81 plus 1 on the back here. All right. And so just changing that form up a little bit. Let's go to the one right below it. Let's go to number 4. Now, if you know your transformations, number 4 can be a very fast problem for you. Again, this is something we kind of experienced on the test that we just had. All right. So if I have a graph here, let's say it looks something like that. All right. This plus 3 at the back is going to shift it up 3. So I would go up 1, 2, 3. This plus 2 on the inside with this square root is going to shift it what? To the left 2. So again, a lot of kids are thinking that plus 2 goes right, but really it flips on the inside, so it's going to go to the left 2. And so I would have the starting point really right about there. And I would have a graph that looks something like this. And that's all I really need to find domain and range. All right. Again, that point is a little bit to the right. Kind of want a little bit above here, so let me put it right there. Looks something like that. Now, what is our domain? What is our range? Well, domain, I always tell kids, it's the x values, and it tells you how wide the graph is. Well, if I'm going left to right here, well, I'm looking over here at the left, and it starts at -2 on the x-axis. So it's including -2 because it's a solid circle. But again, if you were to hold your hand up right here, you would see that this starts at -2. And does it ever stop going to the right? No, it doesn't. So it goes out to positive infinity. To positive infinity. And now what is my range here? Well, range is how tall the graph is. Well, the graph's bottom is right here. The graph's bottom is right here. So my range would be what? What's the bottom of this graph? Well, the bottom would be including 3. And then how far does it go up? Well, it never stops going up. Even though it looks like it gets flat, it's always increasing here. So it's going to be infinity as well. All right, it's going to be infinity as well. And if you wrote it, this is interval notation. All right, and then set notation. Again, a lot of kids miss this on the test. If you want it in a different notation, there's the other one. And this goes with this, and this goes with that. All right. And so again, it can help you out a lot if you kind of know your transformation. Now, granted, number 6, you're probably like, I'm not quite sure. It looks kind of confusing. Listen, it's okay to go to a calculator to kind of get that graph right. Okay, I'm okay with that. But you can see the -3 is going to shift it down. The 1's going to shift it to the left. The negative's going to flip it or reflect it. And then that 4/5 is going to sort of compress it a little bit. All right. Awesome. Let's go to some of the new stuff. All right. Let's go to some of the new stuff here. My plan is to work a couple problems with you here and just kind of explain. So it says sketch a graph. So we're going to sketch a graph of each function here. We're going to state domain and range. And then we're going to identify, I said relative. I should write relative here. Relative maximum and minimums if possible. All right. You'll see on some of these you don't get relative max and mins, and we'll kind of talk about that a little bit. All right. On some of these, really the hard work and really the cube root functions, the work is put in by just graphing it. The other two come pretty standard, and we'll talk about those as we kind of work through it here. So let's say we have y equals the cube root of x plus 2. Well, I know from some of the things that Mr. Sims has taught me that this plus 2 on the inside shifts this graph to the left 2. All right, shifts it to the left 2. And would move it right about there. Now, you may be wondering, well, Mr. Sims, what does this 3 do? I mean, surely that has some sort of impact on the graph. And yes, it does, but it's not really a transformation that we would take into account. Like, we don't consider this 3 a big 3 out front or anything like that. Remember, your parent function here is simply this. So that is already part of the function. So it's not really a transformation, that 3 per se. All right. And so really this graph sort of starts at this point. Now, what does this graph look like? If you were to graph it, kind of looks like a real flat or sort of winding, sort of chicane-like picture. So the question becomes, how do we get other points? All right, how do we get other points? And what is this point that I've already found here? What is this point that I've already found here? Well, let's take a look here. You can do this the old school way. I kind of like the old school way, and I like for you to know both methods. I think they're both are helpful. All right. So if I have my x and my y values, well, clearly I've already found one of my x values and the corresponding y value. So I'm going to put -2 right here on the graph, and I know that it corresponds to 0. All right. The question becomes is if I plug in other numbers into either this function or graph it even, what would I get for the y value? Well, if I plugged in, let me just start working my way down. If I plugged in -3 here, whether I plug it into a calculator and solve, or if I graph it, whatever works. But if I plug in -3 into my equation, I would get -1 for the y value. Again, all I'm doing is plugging this into this function. You would see, okay, -3 plus 2, okay. What does that look like? You may think, well, teacher, I'm getting a negative underneath that radical. Don't worry about it just yet, okay? Don't worry about it just yet. Cube root functions are different than square root functions, all right? They're different, all right? So getting a negative, Not such a big deal here. And so what you would get is what? -3 and -1. And so you go to your graph and kind of plot it here. We'll just go ahead and put that point on there. And let's do -4. Well, if you do -4, it gets kind of a little bit hairy, as we say, right? You do -4, you're going to get -1.25992. All right, a fairly long decimal. All right. Again, if you want to put a point on the graph, you can. So go to -4 and kind of right around there, put a point. And basically, we've kind of knocked out our negative numbers. Let's pick a negative number that's greater than -2, which is -1. Well, if you plug in -1 here, you're going to get that it equals 1. And so where would you put the point? You put the point right here, and you're kind of off. Now, again, I'm plotting a lot of points. And with cubic graphs, I typically will. So let me kind of section these off a little bit so it's easier to see. Well, let's do another one. Let's do 0. Well, if you do 0, you would notice you get 1.25992. Okay, so I go to my graph, I put that point, and you're probably thinking now, okay, I'm starting to see something here. The great thing about these graphs is they tend to be symmetrical. All right, they tend to be symmetrical. And what point are they symmetrical around? Well, they're symmetrical around typically sort of that starting point that if you're able to find is super important. All right, now you're going to learn in calculus and maybe even in pre-cal, all right, how you can find this point by doing very little math. All right, for the sake of today's stuff, we're just going to use those points to kind of get a function that looks something like this right here. Granted, is that graph completely accurate? No. Again, if I wanted to make a graph completely accurate, I would take all the points all the way out, all the way across the graph to the left and to the right. All right. But for me personally, as a math teacher, again, we're not really concerned about making it perfect just yet because we're not building rockets. We're not doing rocket science here. All right. But I at least get a general picture of what this graph looks like. Okay. And so that's a graph. Now it says state the domain and range. Well, the nice thing about domain and range here is that, think about it, domain, does this graph ever stop going to the left or to the right? No. So this is -infinity to +infinity. You may say, well, okay, teacher, I get that, but what about the range? Well, here's the thing. This graph never stops going up or down either. So it's -infinity to +infinity. I think you're starting to notice a pattern with these, all right? And you will notice a pattern, all right, with the domain and the range. Can those domain and ranges change? Absolutely. Absolutely. In special case scenarios. All right. Now, what's the last thing? What about relative mins and max? There are no relative mins or maximums. No minimums. No, I should say no minimums. No relative minimums or relative maximums. No relative min, no relative max. We will talk about that when we get to x cubed, which will be our next problem. But really what I wanted to show you here is how this sort of reflects. Again, you can probably see it. Again, I probably don't need to show you. But notice how these two values sort of match each other. Notice how these two values match each other. Very similar to what a quadratic graph would do and how they sort of reflect across. Okay? Let's go to another one here. All right, we'll do one more and then I'll turn you loose on this. One more. Let's go to 13. Now, 13, granted, you can do this a lot of different ways. Well, with 13, 14, 15, 16 here, you can do this a lot of different ways. You can go ahead and you can plot points, like you can plug in 0 for x here. All right, you'd see if you plug in 0 for x, though, all this is going to go away and you're going to be left with -106, which is going to be way down on the graph. So it's not even going to fit on the graph. All right, but maybe you do a test point with 1 or 2 or whatever that number is going to be. All right. Now, what I did is I just used Desmos here, since again, this is kind of a weird, funky equation. You notice the others don't look near as bad, so you'll probably have a little bit more success. But if you use Desmos here, you'll see this is kind of the graph that I get. And so I can transfer these points onto my graph. And we're going to talk about one point that's not even mentioned here. All right, we're going to talk about one point that's not mentioned. So I'm going to transfer, after I graph these, onto my graph here. So one of the points that I noticed was that it had an x-intercept right around 2.8. So like right around there. And the graph went up. Again, maybe you have to go back and rewind the video, but the graph went up to 4,6. So it went up here, and it was going down here forever. All right. It went to 6,2. Yeah, I'm trying to do my best here, freehanding it. And then it shot back up, something like that. Oh gosh, I did that on the wrong the wrong grid. Here, let me transfer it over real quick. Hopefully you didn't write it on 14. So 2.8 up to 4,6. So something like that. And then 6,2 is right here. So it kind of comes down, touches it, and then goes back up forever. And it does go down forever here. So what are these points, and why are these points super important? Okay. What are these points and why are they super important? Well, hey, x-intercept, super important, could mean something as such as where an object lands, stuff like that. What about the top here? Okay, what is that point? And what is this point? Now, again, I'm not super particular about how you get the graph because I understand graphing this is going to make it way faster and way more accurate on your end, okay? So what can I do? Well, you can make a table or graph, but there's one point that I want to point out before I go into anything else. I want to talk about this point right here. This is a point that I call the point of inflection. The point of inflection. You'll notice on the graph here that you kind of get that point just a little bit. It's right here. I can get it to pull up. 5,4. Now, that point is super important because if you can tell, something you maybe learned in geometry is that if you were to rotate this symmetrically, you would see that it matches with the graph sort of on the right side. This is basically kind of like a point of symmetry, so to speak. Now, the point of inflection is great, and you're going to learn how to find the point of inflection in calculus and why that point is important with graphs. All right. Why that point is super important. All right. But that's the point of inflection. And so that's super important. Now, we've got the graph. What else do we need to do on this problem? We need to find domain and range. Well, domain and range. Again, does this graph ever stop going to the left or right? No, it's going down and to the left forever, and it's going to the right and up forever. So domain and range on this one, pretty straightforward. Negative infinity to positive infinity. Not a whole lot happening there. All right. But it's good for us to kind of see that. It's good for us to kind of see that. Can those domain and ranges possibly change? Yes, we would have to adjust this function, though, maybe a little bit to get a different domain or different range. Now, the other question was relative min or relative max. All right. Now, I'm going to kind of emphasize this is going up. What is a relative min and what is a relative max? Well, I'm going to go ahead and write that down real quick. I'll write relative min and then a relative max. Again, it's short for relative minimum, relative maximum. So what is a relative minimum going to be? Well, a relative minimum means if we're taking a piece of this graph, where does this graph seem to hit a low point? All right, where does it seem to hit a low point? So it's relative to the graph that we can see. So what is the relative minimum of this graph? Well, it's going to be this bottom point right here. All right, again, just like a minimum in a quadratic, the relative min in this is going to be 6,2. It's a relative minimum where the graph goes down and then goes back up. Is that the minimum of the graph? No, but it's a relative minimum because the graph within this sort of frame that we're looking at here has a minimum right here. Again, the minimum could be any number basically less than going down from this sort of function, all right? But a relative gives us this, okay? Again, you'll learn in calculus how you can solve for this point without having to even use a graph and using what you have up here. All right. That's a relative minimum. So what is a relative maximum? Well, a relative maximum is a relative high point in the graph. So where would the high point be? Well, it'd be at 4 comma 6. That's a relative maximum. Again, is it the max of the graph? No, but is it a relative maximum? Yes, it is. Again, think of the word relative meaning sort of relating to. Well, if we're relating to this graph here, the maximum that we're looking at is going to be that point right there. All right. And you've got everything you need. You've got your graph, your domain and range, and your relative min and max. So the bottom four can go pretty quick once you get a graph, again, much like the ones before. Um, so yeah, again, I'm going to remind you, I will be available for questions tomorrow from 10 a.m. to 11 a.m. So if you have something, let me know. I'll just be hopping on my Zoom. Again, please reach out if you need me, if you need help on anything, guys. All right. I'll see you later.